Good afternoon. Today we'll see a practical demonstration of application of machine learning on geospatial data. In previous lecture, we have seen how to use machine learning for geospatial data. Theoretically, we have seen one machine learning algorithm named random forest. Today we'll perform this algorithm over some geospatial data. The data for this exercise you can download either from any satellite source or you can go to this you can go to Earth Explorer. Here you will see a login option and sign up option. You create an account here and go to your area. For example, I want to download data for Delhi, so I will search here. To this, I zoom to Delhi area. Now go to data, and here you need to choose from which range data you want to download. Let's say I want to download data for starting from April 22 till May 6. Now you go to data sets and you can choose download any data. You have Sentinel data available here, Sentinel-2, Landsat data. Within Landsat you are having multiple collections. So you can download Landsat 8, that is latest one. You select here the results. You will get the satellite scenes available in this area. And click here to get the footprint, the image belonging to this area. So you can go to this location and download some satellite image here. You go to this download option. And here from product options, you will see this bundle or band by band data is also available. Suppose you are interested in only band 1, 2, 3, 4, then you can download separate bands. Otherwise, click on this, the entire bands, all 11 band data will be downloaded. So this way you can download data for today's exercise. So now I am having the Landsat data available with me. So we'll use that data. When you will download the data, you will notice that all the bands are downloaded separately, like band 1, band 2, band 3. This is band 1, band 2, band 3, band 4, band 5, band 6. So these data sets, these bands are downloaded separately. So you need to stack them. So to stack them, you need a software, GIS software. You can go to QGIS, and here in raster, miscellaneous, merge. From here, choose the bands which you want to merge. So 7 bands we will consider. By the way, Landsat is having these bands available. And band 1, band 2, names, yes, names are written here. So up to band 1 is for aerosol detection, ranging from zero point 0.4 to 0.43 to 0.45 micrometer. Band 2 is blue band, band 3 is green band, band 4 is red band, NIR, SWIR. Then band 8 is panchromatic band. Since we are having RGB separate bands, then additional panchromatic is not needed here. You can keep it, that is not a problem, because data redundancy is not a problem in random forest method. Then this Sirius band to used to detect Sirius cloud. Then thermal infrared band, that is not needed here. We will be performing today image classification over this Landsat. So this is used to calculate temperature, not useful. This will give uh, wrong classification if utilized in this, because thermal emission will be different in different regions. It is not too much dependent on, it is dependent on the temperature of the surface. For hills, temperature will be lesser, so it will create problem while classification. So we'll keep our focus from band 1 to band 7 only. So that is why I told to select here band 1 to band 7. Open, okay. Place each input band in separate. Uh, place each input file in separate band. So basically, you can you are doing here stacking the image, so that instead of having 7 scenes here, 7 bands separately stored, you will have a single band stored. You will have a single file having all the bands, like this one. So here this single file, this is having all the bands. See, you can check its properties, information. it is having 7 bands in the order selected. So right now things are not visible. We'll make false color composite. False color composite is made by uh, using NIR red and green bands. So for lines at 8, FCC combination is band 5, band 4, band 3. Band 5, band 4, band 3. So now you will see FCC. Red color is representing vegetation, dark red is for forest, pink is for cropland, and this color, this is for built up area. So basically, we have seen yesterday for machine learning model, we need a lot of data to train the model. So here our objective is to perform classification. So for classification, training dataset need to be created. So what we will do, we'll create some points here and will identify the use land cover class corresponding to those points, and those points will be used for classification later on. So ideally speaking, when the training dataset is created, number of points in different class should be kept as many as possible. The sample should not be, random, because here you can see a lot of area belong to forest area. So if I will create random points, so many points will belong to forest and built up is very less. So built up representation will become very less in samples. So basically balanced samples need to be created representing each class or desired class. So that you can do by creating manual samples, but today we'll generate random samples, 100 random samples, and corresponding to those samples, class will be identified. One more thing you will notice here, this is snow and these are clouds. It is difficult to separate between snow and cloud from MSS image, multispectral image. So a derived product NDSI is used normalized difference snow index to differentiate between snow and cloud. So that can be used derived product. But right now we'll focus on these 7 bands only, no derived product. So first of all, we'll create a small boundary around this. So I have created, no, I do not have the boundary. So I'll create one boundary, go to layer, create layer, new save file, then boundary. Geometry type, polygon, coordinate reference system. Let's keep it same as the layer system. Layer is having coordinate reference system of WGS84 and UTM44. Same system is kept there. Now edit it by going to right click and toggle editing. Now you will see these options are highlighted. Add polygon feature. Now we'll make a polygon around this boundary. So one polygon is created. I have created this polygon because I want to make sure my generated sample points are confined inside this only. Now we'll go to vector, research tools, and random points inside a polygon. Here input polygon layer is this one, and how many samples you need? I need 100 samples. You can make 200 samples, 1000 samples. It depends on how much data you have. Give output file name here by clicking here, save to file, give output file name and run it. What it will do, it will create 100 sample points randomly inside this region. Now open attribute table of this point file, right click, open attribute table here. You are having ID field empty, will enter our classes here itself. So what we'll do, we'll assign ID 1 for snow, for forest, for waste 2 will be assigned for wasteland. We'll assign 3 for forest, for built up area, and 5 for this nomenclature will consider. Why I am considering 1, 2, 3, 4 instead of writing snow wasteland? Because we know the algorithm needs the numbers, not the names. So if we'll write snow, wasteland, forest at the later stage, while performing classification, these names need to be converted to numbers. So for example, if I will start with this point, it is not known this is snow or cloud, so we'll consider them snow only. Or we can write snow plus cloud for 1. We need to start editing for this, toggle editing. Open attribute table of this table is open, and from here select show selected features only. Now this is feature selection tool. This one will go here, select this feature, and here we'll see this is highlighted. Now what is this? This is snow or cloud. So we'll write here 1. Enter. Now this one, this is again snow or cloud. We'll write 1, enter. Now we'll see some other point. This is forest by the way, but shadow region. This is another point. Let's see what is this. This is not forest at all because okay. So we can give here name wasteland. This is shadow region basically. So we can assign it shadow or some other class. We'll write here 2 Then this one, red color, this is forest. Here we'll write the value for forest we have decided is 3. So here we'll write. Now we'll come down, go to this location. This is again a forest class, red color. The point is somewhere here. This is more, this is like uh, croplands. They are not very red. For cropland, my ID is 5. Here this point, it is built up for cropland. We'll write here. For built up it is 4. For built up it is basically this way we have to see all the points and just write their classes. So this is how our training data is made. So we need a lot of efforts to make the training data. From the image, if you are making the training data, you need to learn about image interpretation. That is one thing. Otherwise, you can take help of Google Map also. Because Google imagery, that is high resolution imagery compared to this one. So here you may not be able to identify something very clearly. For example, this one, this is river, this point. Somewhere you may, this is again river, water body. You can have another class here, water body. Suppose this point I am not able to identify what is this point. One thing is we can adjust the contrast here from symbology. These color rendering options we can tune. Other one is open Google imagery in background. So for that you need to go to plugins, manage and install plugins. You need to be connected to internet, and here you search for quick map service. That is one word, quick map services. You install this plugin. So right now it is installed in my system, so I am getting option to upgrade. If it is not installed in your system, you will get install plugin. By pressing install plugin, you will get the plugin here installed. That you can locate under web. You go to quick map services, then Google Hybrid. So what it will do? Open Google imagery in background. So Google imagery is very high resolution imagery. You can see from here it is cropland. From here also you can see if you are having good image interpretation skills. If you need a high resolution data, you can check with Google. It is cropland, very clearly seen in the Google map. If some point is somewhere here, then it will be built up area. So with the help of Google, you can assign this point to cropland category. You can disable image to see what is in the background. You can zoom out to see that in which area, for which area this image belongs. This is Kedarnath area, this one. So obviously there will be snow. Here this area is not in lower side or Himalayas. So here you will not have snow. These are the clouds. If NDSI you will consider, can easily remove these clouds. So one by one at the end, you will have a file, a training file basically, like I have created earlier, where all the points are having some class value. So I have 100 points which is having class value. You can create this 100 points as discussed. Now what is next? How this training will be done? So right now what we are having a point location and its class type. So the class type or LULC class, that is the label. Yesterday we have seen what we need. We need a feature set, that is also known as feature vector, that is the measurable uh, property of uh, the target. So that is here. Feature vector is your bands, your values in your bands. You are having 7 bands basically. So if you click any point, you will get a table. These values, basically these pixel values in these bands, they are your features. And if these are the values for a feature, that feature will be known as whatever label is assigned. So what we have to do now, we have to extract this pixel value corresponding to these points from the image. So for that, now we'll go to Jupyter Notebook. So type CMD here, wherever you want your Jupyter Notebook, wherever you have data, then write Jupyter Notebook. So now we'll create this notebook is open. Now we'll create new notebook. Name will be given, let's say, name we can give. First of all, what we need to do, we need to write, basically import whichever library is needed, since we have to extract values corresponding to the points from the raster image. So for raster, we need GDAL. To import GDAL, we need to read vector file. So we will use geopandas, import geopandas as GPT. We need numpy, so import numpy as np. What else we need for plotting? We may need matplotlib. And what else? These libraries are needed for reading the data and data pre-processing, you can say. Now we need something, some library which is having the desired model. So random forest is inside sklearn library. So use from sklearn Model selection will use to select the model. We'll see how model is being selected. These libraries are imported. Now what we need to define path of the image. So image path, name of the image. I have this one. The path of the point file. So you keep path of the point save file. So this one point.shp. That is name of the save file. It was told if your notebook file and these files to be read, they are in the same folder, then you can write just name. If your files are located somewhere else, then you need to type the complete path of these files. After this, what else? We start reading the raster file first, that is TIFF image. How do we read? Data source equal to gdal dot open. This will open our image. Now the geotransform parameters will also be needed. So we'll store geotransformation parameters in trans, and this are in data source. So ds dot get and dot geotransform for coordinates of top left corner and width and height. We'll read the data also. We'll read data in the form of array. ds dot read as, this will read image and convert it to array format. We are doing this because we need the data values for training. We can see shape of the data.save. It is expected that there will be 7 bands and some rows and columns. That's what you can see. Here you are having 7 bands. These many rows and these many columns are present in the data. But also this has plotted band 0. Band 1 also. You want multiple bands to be plotted in the same image, we need to use subplot command. right now in plotting phase. Of some point 20 dot let's just plot spectrum for some point here to 5000 column 2000, something like this one. These are the RGB bands. One is red, sorry. This 3 is red, 4 is NIR, 2 is green, 1 is blue band. This figure is representing vegetation. This spectral plot is representing vegetation. Because vegetation is having a larger value in NIR. This is NIR and reflectance value is higher. And where we read the save file in df underscore file. DF is having these categories: ID, name, nothing inside, that is blank. Then geometry file. Geometry file is referring to, sorry, geometry column. Geometry column is referring to the geo coordinate of the point. So our objective is now to add here other 7 columns which is having value from all the 7 bands. So corresponding to this location, value from 7 bands, corresponding to this location, value from 7 bands. In previous lecture also we have seen the geo transform, which we have seen here. This trans. It is having coordinate of top left corner. So longitude of top left corner, then latitude of top left corner. So basically here, this one. So from geo transform we get this one. Now we are having image of this kind where rows and columns are there, and this image is converted to array format. So suppose here 1 2 3 4 5 6 6 columns are there and 5 rows are there. So this image is converted to array of 5 cross 6. There are multiple bands, 7 bands, so 7 bands. So basically there are 7 arrays, one behind other. If some point is somewhere here, so what will be the corresponding value from this image? So for that we want what? We want row and column number corresponding to the point. So how will you get row and column number? Here we are having x0 and y0 available. This point is having some value x1 comma y1, let's say. So if we subtract x0 from x1, we'll get the distance between here and here. And if we divide that with pixel size, this is pixel size, then we'll get a column number. If we subtract y2 from y0, y2 is lesser, y0 is higher. So if we subtract y2 from y0, we'll get this distance. We'll get this distance. And if we divide this distance by pixel size, we'll get the row number. This one is row number. So basically, we have to subtract coordinate of the point from the origin of the image and divide by pixel size to get row and column number of the array. Once we have row and column number, we can simply pass the index here. Data is our array. Here data is our array. If we know the row and column number, the first index is for band. So let's say I want value from band 2, from where row number 1000, column number 2000. If this is known, we simply enter here and we'll get the value corresponding to that point. So for this we need to write a function which should do this job. Then write here def val function. Capital X, let's say this is input of this function. What we'll do here, this is our data frame. We'll pass this data frame to this function and we should get the value from the raster corresponding to these points. So here X is our data frame. We'll pass this data frame df inside this function. So X is our data frame. So for entire data frame, what we need, this geometry column only. So longitude from this geometry column will be x dot geometry. X is data frame. Dot geometry will give, and when we'll pass here, we'll write get well, and inside this data df will be written. So here ultimately will be data frame dot geometry, which means this column. And from this, what we'll want, first x value, then y value. Dot x, all x will give x value. Latitude is y value. X dot geometry will give us latitude and longitude. How will get row value? Subtract y coordinate of point from the origin. So row value will get subtract y coordinate. Y coordinate is latitude from the origin. Y of origin. Y of origin is this one. So index value 0, 1, 2, 3. So trans of 3 will give us y coordinate. Trans 3 will give y coordinate minus latitude divided by pixel size. Where is pixel size? This second value. So trans 1 pixel value may get some fractional value also. We will convert them to integers. For column, what we need? For column number, what we need? Subtract x coordinate of point. Subtract from x coordinate of point the origin of image. So x1 minus x0. If here coordinate of point, that is longitude, minus origin, so that is trans 0. Right? Pixel value. So this way we have got the row and column value corresponding to this point. We'll return the pixel value. How? Data row column. This should return the data value from this array at row comma column value. But here you are having 3 index for data array. If you see data.save, you will see 7 here, that is band. So band by band information you will get. So for that we need to pass some other integer named k, let's say, which will be the band number. Then we'll get corresponding to this particular band and particular row column, we'll get data value in return. We'll run this. We'll not get anything from this until we call this function somewhere. Now, band by band we have to write, we have to get the value. So for k in range 7. Yes. And k, if I am doing, it is printing 0 to 6, 0 for band 1, 1 for band 2, 2 for band 3, 3 for band 4, 4 for band 5, and 6 for band 7. So k can be the, if we are calling the function here, k will be the band number. But as I told, this input for this function is data frame itself. And we want to run this row by row. For one point, it should get the data. For second point, it should get the data. There is a function named apply. F dot apply. What apply? Get val, comma. How do I want to apply? On column axis. On columns, it will be applied. So this what will do, this df is input for the function. GetVal is name of the function. It will be applied column wise over this geometry column, because geometry is getting extracted here. Now this will get value corresponding to these points in return, but what else we want? We want this value to be stored somewhere. What we'll do, for band 1, we want it to be stored in band 1. So here we need to define band. We can simply write B1, B2, B3, but we want this to be written in the code. So we'll do k plus 1. So for first iteration, k will be 0. So b plus gives b, sorry, b here, let's say k is 0, inside you will get 1. So str1, so you will get g1. str will convert integer to string, and these two strings can be added for the strings. So it's done. Now let's print df. Here you can see you are having values from the bands b1, b2, b3, b4, till B7. So this will be our feature vector and this ID is our target. The same feature equal to our features are these. So we will select them. Comma, P2, B1, B2, B3, B4, B5, B6, B7. Target. Target is F. We want values, not data frame, not values. And here, int array of size. What is the size? 100 rows and 7 columns. Just check it out. 100 rows and 7 columns. And target, that is a single array. Now what we need to do, we need to define the model. Till now what we have done, we have made our feature vector and target. That is the required for training the model. Instead of having these bands, we can have any number of band, any derived product we can have here. That's up to you to decide which kind of info is needed. We will go with this. Next step is to define the model. Let's say I want a model name forest. To this model is inside in symbol package. In symbol we have imported from here, from scalar. What we want? Random So if you remember the lecture, few things I told, number of trees need to be defined, estimators, n underscore estimators of trees. Let's say I want 100 trees, then minimum sample split, minimum samples needed to split it can be a value less than or equal to number of features available. So number of features in feature vector are 7. So it can be less than 7. We can keep some value 4. Later on this need to be tuned. These are the hyperparameters. Then maximum depth of the tree. Maximum depth of the tree can also be defined. Let's say I am putting 7. This also can be tuned. We can give some number. That for each randomization, random samples picked are same whenever we rerun this model. Jobs, number of jobs, or let the system manage. This is for training in parallel and sequencing. So you can put -1 number of jobs. System computer will manage how many jobs need to be fired. random estimators. Minimum samples split. When you can see properties of this function, you will get the names. So till now, this definition is done. Now what is next? Pass your training data here. What fit? This forest is this one. Now what we have to do, we have to pass this data inside this model definition. Forest dot fit, how to fit, feature, something is so here it is given 95 accuracy. Why accuracy is very higher? Because this accuracy is tested based on the training sample itself. So it is not a good way to test the accuracy, but it will give you some idea. So for accuracy testing, can do cross validation or some other or some data using some data which your model has not seen. You can also see which feature was how much important. Is giving importance of the features and fractional numbers. Some features are very less important like SWIR2 and SWIR1. They are directly not important, but when you will make NDSI, then for cloud and snow separation, they will become important. Basically, their derived product will become important. Independently, they are less important. You can see some train the model, sorry, tune the model. Let's say till now we have given 100 estimators to 100 trees. Basically, estimators are the trees, 100 trees to train the model. Are they optimized or we need to tune them? So for that, we need to make a list array of many estimators, 1 to 250, let's say, at interval of 10. What it will give? It will range. This will give the range of trees, range of values. We'll consider them as trees. So we'll need plot this one. For each tree, we find out the accuracy and plot it. Scalar this validation curve is imported now. We will plot the validation curve basically for different trees. Here testing will be done based on the cross validation. how validation curve based on the model forest. Does it like which parameter we want to tune here? Parameter name, number of estimators. How ranges of this equal to how CV equal to 3, cross validation equal to 3, which means the training data will be divided in three parts. First part, two parts will be used for training, and second part will be used for the third part will be used for testing. Then first and third will be used for training, second will be used for testing. How score I want based on accuracy. It is classification. Classification score can be measured in accuracy or regression. If it is regression, then accuracy cannot be used. Instead of this, uh, RMSC or absolute error may be used. This will do this and got something this and under. There are some classes which is having only one uh, sample. That is why this warning is coming. So this is done now. So let's as I told, it is CV3, which means for each time score is given. What we can do, we find out mean of all these three. So test equal to NP. This will find out that x is equal to 1. This find row wise mean. Same way we need to write for train. Train underscore mean equal to dot mean for train score. We can plot this. Plot want to plot on x-axis or on y-axis. Test mean. And what is this? Let's make it plot train score also. Same on y-axis, train mean, label, mirror, spelling of label. So here you can see this red color is for testing and the black color is for training. So obviously for training you will notice a larger accuracy. Why? Because the data used for training, the same data is being used for finding out the accuracy, which means that data used for accuracy model has already seen. So you will see higher accuracy. The red curve model has not seen the data because it was divided in three parts. So that is why if model has not seen the data, if new data is coming, so you will see a lesser accuracy, little lesser. There should not be so much deviation. Like training accuracy is 95 and testing accuracy is 50. That is the condition of over training, overfitting of the model. So this way what you can see, if you are increasing number of trees, on x-axis is number of trees and y-axis it is accuracy. So if you are increasing number of trees, the accuracy is increasing. If you reach some limit here, it's around 25 or 20. So after this, even if you are increasing the number of trees, the accuracy is not increasing. So which means optimum number of trees should be around 25. So what you have to do here, in place of n estimators, you write 25, then train it again. Now our trained model is ready. What we want to see prediction of some pixel. Let's say this pixel value. I want to find out its class. So I will click here. Copy feature attributes. Just for testing, I am doing this copy paste. Otherwise, you need to write the code here. These are the values corresponding to some pixel, which is forest. I am taking this data from QGIS because here you are seeing the visually what is the class value and what is model predicting. Right. Here we'll paste these 6 values and we need to resave them, -1. And we are reshaping to get the shape like this, which means row is 1 and column is 7. So that for that we have done reshaping. So now how prediction will be done? Forest is name of our model. Forest dot predict. What to predict? Pass it here. And what we got? 3 in return. What is 3? If you remember, 3 was our forest class, which means it is predicting correctly. Somewhere here the point was taken that belong to forest. So which means prediction is being done. The next step can be you you do prediction corresponding to each pixel. We are having this data dot shape. If you do 7 bands and these many columns. So for that, what we need to do for range of rows, the column in range, the column in range this. So what will be our spread here? That equal to data. All columns, we want all columns, so we will write data column and row comma column value, and we need to reshape it to 1 comma minus 1. So this will give in return this kind of array. It will give. So we can test also what it is giving. Row 8 1000, 2000. Get the same kind of array. So this array will get for each row and column. Then what we need to do, will predict this by passing this array in this in our model. Forest is our model. Predict is the function which is passing this array to the model and will get prediction in return. This predicted value need to be stored. This predicted value need to be stored somewhere. So for that you can create out dot zeros. What kind of zero? These shapes. Will be our output. So we'll put our output value in row and column of this. So at the end we'll get predicted value. So it will take time to do the prediction because so many pixels are available. This prediction time can be optimized using parallel processing and all, but right now in sequential pixel by pixel processing it will take enough time. So at the end we'll get a classified image. Basically we'll get one array. This array need to be written to TIFF file or IMG file, and I have told how to write array to a TIFF file in first lecture, so you can refer that later. So at the end we'll get our classified image. This image classification can be even improved with improving the training sample. Here you have seen training sample was there, but it was not very good. If you improve the training sample, improve the feature vector and do these things, you will get a better classified image. With this, I end this class. If you have doubt, you can ask.